Okay, we are about to embark on Newton's second law. So Newton's first law, that first law was dealing with constant motion, where we said something at rest was going to stay at rest, something in motion was going to stay at rest or stay in motion unless we had an unbalanced force working on it. So kind of opposite to that, we're going to now work with Newton's second law, which is going to say if that's not true, if we are going to create a bigger and bigger force, what is likely to happen to our object? So if something doesn't move with a constant motion, what kind of motion is it going to have? Constant motion. What kind of motion is it going to have? Let's hear from
an increase in motion or decrease in motion.
Yeah, and what's the word that we use for this?
Acceleration.
So we're going to be dealing with acceleration. All right, great. So let me show you how we're going to kind of develop Newton's second law. What kind of lab experiment we're going to see here. So here's what we're going to be using. So if you want to, on page 183, where it says draw and label a picture of the setup, that's where this might belong. Okay, this is going to be the track here. And then we're going to use an instrument, a sensor that I don't think we've used before. It's called a motion detector. So that's what this thing is. So this motion detector is a device that's got like a little speaker here, and when something is in front of it, it can measure by sending out pulses the distance. So if I had something here versus here versus here, it'll be able to figure out how far away that object is. So this motion detector is going to get connected to a computer. And that computer is going to be able to record the distance of that object. And since the computer can tell time, it now has these two pieces of information, distance and time. The computer can figure out the velocity of that object. Now, what is the relationship between velocity and acceleration? So Sophia, what's the relationship between acceleration and velocity?
Acceleration is the velocity like increasing per second, or so like velocity would be like meters per second, but acceleration would be meters per second per second. Okay,
so if we're just looking at the units, we're really looking at the change in velocity every second. So how quickly is the velocity changing? So if the computer has information then about distance and time, it's going to be able to calculate velocity at various spots, and therefore we're also going to be able to get at acceleration. All right, so there's our first setup. Then we're going to have a pulley right here. So we've used pulleys before. We're going to have a pulley there. And then we're going to have our cart. So let me get a new color here for our cart. Okay, here is our cart. And on top of that cart, we're going to be able to place some mass. So you've used carts here. We're going to put some mass on this cart. And now we're going to connect that cart via a string over the pulley. And on the pulley, I'm going to place that pan. Okay, so the first thing we're going to do is we're going to run an experiment where we are going to keep mass constant. And when I say keep mass constant, I'm going to call this the system mass. Now, what do I mean by system? The system is going to be the cart, the mass on there, the string, and this pan. That's what's going to be the system. The track and the motion detector, they're just, you know, places where we're kind of running our experiment. And so this thing right here, this pan, what force is acting on that pan?
Tension.
Well, kind of, Daniel. Go ahead. I'll keep with you right now. So unmute yourself. So on that pan, so you said tension because you mean this pan is going to pull on this string, right?
Yeah. Mm-hmm.
So, but what's causing what's my question here? Why is there a tension being created on that string? Because what does this pan want to do?
There's gravity.
There's gravity. There's the force of gravity is pulling this down. Now, if I were to move some mass from the cart and put it over onto this pan, what would happen to our force of gravity? Daniel? If I were to take some mass and move it from my cart and put it on the pan, what would happen to my force of gravity?
It would be stronger on the pan, so it would pull the cart.
So it would then create a bigger force of tension, which would then pull the cart with a greater force. Here's the most important question, Calvin. If I move some mass from my cart over here to my pan, have I changed the mass of the system? Do I still have the same amount of mass with my cart, my masses here, if I just move some of it from here to there?
Well, you still have mass in the cart, but it's not the same.
Ah, but my system is my mass just of my cart.
No.
No, it's of all the mass of the cart and these masses and the pan and the string. So if I move my mass from here to there, is the mass of the system the same? The total mass. Would you agree?
Yeah.
Yes, great. That's the main point that I wanted to make right there. But every time I move some of my mass from here to there, is my force going to change? Let's address that question to Charlotte. Every time I move some mass from here to there, will the force change? The force of gravity.
The force of, since the mass is the same, it should be like the same, but it's kind of like acting differently.
Yes, I like that explanation. That if I put some mass, say I had a little mass there and a little mass there, and I took this one and I put it down here, would there now be a stronger pull on that cart?
Yes.
And am I really pulling the cart, the masses, the string, the pan? Is all of that being pulled at once? Yeah, that is. So now I could take more mass and I could move it from here and I could put it down there. What would happen to my force of gravity then? Let's go to Carolina.
It would get bigger.
It would get bigger. If I take more mass and put it there, but my system mass is going to stay the same. So what we're going to be measuring here is we're going to move mass. We're going to move it from the cart and put it on the pan. And when we move, let's say when we put more mass on the pan, that means we're going to increase the force of gravity. And our question that we're asking is going to be, as we increase the force of gravity, what is going to happen to acceleration? So our question is, let's write it down. Our question is, what is the effect of increasing force on acceleration. We could even add here when mass is constant. Tomorrow, we'll change mass and keep force constant. So today, we're going to look at what happens to acceleration when force is constant. So what's our independent variable for our experiment here? Let's give that one to Nick. We're keeping mass constant.
Oh, force.
So it's going to be force. Force is the thing that we're going to change by moving mass from the cart and putting it on the pan balance.
Yes.
All right, so now with that explanation, let's go to page 183. You're probably already there. And let's get our table going down here. So we're going to use our data table. So the first thing we're going to do is I'm going to have a column labeled mass. And that's going to be the mass in grams. So fill this out as we go. And that mass in grams, I'm just going to make a note down here. This is the mass that we put on the pan. Because by putting mass on the pan, what are we really doing? That's going to be resulting in more of a force. So then, of course, in physics, what do we always use mass? What
Kilograms.
units do we always use mass in? Ava.
Oh, kilograms.
We always use it in kilograms. All right, then once we have our mass, we can use that to figure out force. For example, if I know what my mass is on this pan, how can I figure out my force due to gravity? Who remembers that expression? Whoever does, unmute yourself and chime in.
The mass times the strength of gravity.
There we go, mass times the strength of gravity, which of course is going to be our mass times 9.8. So we'll be able to, and what units would those be?
Newtons.
Newtons. So that's going to be in newtons. So to figure out this column, we're going to use the force of gravity equals mass measured in kilograms times 9.8.
Isn't it negative though?
It is. And today we're going to ignore the sign. We know it's going down. We're just interested in the magnitude of that force and not the direction of the force. So we're going to ignore the negative part of it. Thanks for noting that. And then finally, what's our dependent variable? What are we trying to measure ultimately in this experiment? We're changing force. What question are we asking?
Acceleration.
Acceleration. What is the effect of increasing force on acceleration? So acceleration which is going to be measured, as Carolina told us, meters per second, is going to go in this column right here. All right. Does anyone have any questions that you'd like to ask about our experiment?
Wait, so it's what is the effect of what?
The effect of force
Force.
on acceleration. That's the question we're asking. Ultimately, these two columns, force and acceleration, are the ones that we're going to graph to get at this relationship. In order to change the force, we're changing the mass. We're going to move it from the cart and put it onto the pan, so we keep getting an increasing force.